All right, listen up everyone. Let's dive right into this explainer and completely deconstruct what is arguably one of the absolute most critical topics in the entire Cambridge 9618 computer science syllabus. We are tackling program modules today, specifically looking at exactly how we build procedures and functions from decomposition. Now, whether you have come up through the ranks of the 0417, 0478, 0983, 0984, or even the 2210 syllabuses, you already know that writing raw code is one thing, but designing a flawless, interconnected system is another beast entirely. If you want to design your exam answers like a master architect builds a structurally flawless blueprint, this is exactly where it begins. Every single paragraph you write needs to be a structural masterpiece. In today's session, we aren't just going to look at the dry textbook theory. Oh no, we are going straight to the source to look exactly at what the principal examiners are aggressively searching for when they sit down to grade your papers with their red pens. I see so many students make critical errors here. Let's call one student Alex. Alex overloads their answers with raw computer science facts, practically dumping the whole textbook onto the page, but includes absolutely zero analysis. And then there's Sam. Sam rushes through the paper, completely misses the command word requirements, and drops easy marks left and right. We are going to fix both of those flawed approaches today.
To really understand why this matters so much, I need you to consider this massive, game-changing figure on your screen right now. This single topic, just this one concept of decomposition and modular programming, accounts for approximately 15% of your total marks in Paper 2. Let that sink in for a second. 15%. That is literally a monumental chunk of your final grade. It is quite literally the difference between an A and a C. If your foundational understanding of decomposition is shaky, your entire exam performance is at serious risk. You're building a skyscraper on a foundation of sand. But on the flip side, if you can master exactly how to break down complex, messy real-world problems into neat, functional modules, boom, you instantly secure a massive advantage over the rest of the candidates. You take control of the exam, rather than letting the exam control you.
So, to get us there, here is our logical four-part roadmap for today's session. Number 1, core theoretical principles. Number 2, technical methodology. Number 3, critical analysis and evaluation. And finally, number 4, top examiner warnings.
Let's jump straight into Section 1, Core Theoretical Principles, the academic benchmarks.
Now, what is really fascinating about this slide is the crystal-clear distinction between analytical depth and superficial breadth. Examiners are literally begging for logical, structured reasoning. They will always reward analytical depth over just a superficial, shallow breadth of knowledge. Think back to our student Alex from earlier. Alex memorizes the entire glossary and writes a massive paragraph dumping every single fact about what a procedure or a function is. But that is just superficial breadth. You have to demonstrate precise definitions, absolutely, but you also have to understand the causal relationships within your code. You need to explicitly show how a parameter passed into one module, mathematically or logically, affects the ultimate outcome of another module. To do this, top students use frameworks like PEEL, point, evidence, explanation, link. You make your point about the module, provide code evidence, explain its function, and link it back to the system. Superficial knowledge might scrape you a pity mark or two, but true analytical depth, that is where the distinction lies.
The absolute top-performing students don't just rely on rote memorization. They show a connected, deeply conceptual understanding that easily transfers to totally unfamiliar contexts and other syllabus areas. In fact, if you read the principal examiner reports, they consistently highlight that candidates who actively reference cross-topic connections achieve significantly higher marks. It's like a giant puzzle coming together. Think about it. When you are building a function, you aren't just decomposing a problem in a vacuum. You are often having to extract data from complex binary representations, perform logic gate calculations, or manipulate really specific data structures. Your modules do not exist in isolation, and your answers absolutely shouldn't either. Before we continue, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, moving right along to Section 2, technical methodology. Executing the process. Listen closely. Algorithmic thinking is practically a formula. It relies on a strict, unbreakable four-step sequence for data interpretation and module building. Let's do a quick mental workshop here. Imagine a complex computer science data source on the screen right now. If you had just a 60-second visual countdown timer to extract the core trend, how would you process it? You'd use these 4 steps. First up, step-by-step decomposition. This is taking the big, unwieldy, terrifying problem and slicing it down into logical, bite-sized, manageable procedures. Second, appropriate data structure selection. Are you deciding whether your module needs a 1D array, a 2D array, a record, or a linked list to handle its data? You have to make that choice and justify it. Third, efficient code implementation with the absolutely correct terminology. No vague, wishy-washy pseudocode here, be precise. And finally, rigorous testing to actually verify the results. If you follow this standardized sequence, you are practically engineering a perfect answer every single time.
Now we get to the method marks strategy. This is absolutely crucial to your success. Marks are awarded heavily for clear working and systematic processing. Remember, you must identify key elements, apply the principles, and execute with incredibly clear notation. Why? Because examiners award marks for your underlying process, not just the final result. If you just write down a final output, or if you hastily sketch out a function without showing your systematic processing steps, you are literally leaving marks on the table. You need to show your clear working. You need to present your findings in the appropriate format. When you write your modular code, the underlying logic must be completely visible to the examiner. Don't make them guess what you are thinking. They want to see the architectural blueprint of your mind.
Welcome to Section 3, Critical Analysis and Evaluation, Higher Order Objectives.
Every single time you tackle problem solving in this exam, you should naturally flow through this specific deconstruct, solve, and evaluate cycle. First, you deconstruct. You identify the given information and break it into logical steps. Then, you solve it systematically using the procedures and functions you've clearly identified. Finally, and please listen to me here because this is the exact part students like Sam always rush past and skip, you evaluate and check for reasonableness. Does the output of this function actually make sense within the context of the larger system? If your function is calculating a discount on a $10 item and returns a value of -500, did you check for reasonableness? No, you have to evaluate. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's get back into it.
Look at this incredibly important table on evaluative thinking. Top-scoring candidates don't just pick one single path and blindly follow it to the end. They analyze trade-offs, they acknowledge limitations, and they fiercely justify their decisions with hard evidence. If an exam question asks you to evaluate a specific modular design, you must consider alternative ways the problem could have been decomposed. You have to actively evaluate the limitations of the current design. For example, maybe it uses way too many global variables instead of properly passing parameters by value or by reference. That's a massive security and memory flaw. And whatever decision you make, back it up with hard, undeniable evidence from the scenario. Show the examiner you fully understand the architectural trade-offs of your code.
Furthermore, when doing a comparative analysis in your exam, you absolutely must highlight both similarities and differences, supporting each claim to draw an incredibly strong conclusion. A lot of students fall into the trap of only talking about why one modular approach is better or different than another. But a true high-level comparative analysis requires evidence-based connectives. You need to explicitly state what is similar between two functions, what is structurally different, and then draw a concrete, logical conclusion about their relative importance to the system. You have to weigh both sides of the scale.
All right, we have reached the final and most crucial part. Section 4, Top Examiner Warnings, Insider Pitfalls.
This examiner alert on your screen right now is a massive glowing red flag. The quote directly from the examiner says, "The classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario." This is exactly where our imaginary student Alex drops tons of marks. Let's do a quick challenge right now to find the flaw. Imagine a flawed sample paragraph where a student just defines what an array is without mentioning the system it belongs to. Did you spot the sentence losing marks? Yes, if you memorize definitions without applying them to the specific scenario provided, you will lose those marks. Let me say that again, because it is that vital. Context is literally everything. If the exam question is about a complex library management system, your decomposition analysis must explicitly talk about books, borrower IDs, and due dates. If you just write a generic textbook definition of what a procedure is, the examiner cannot and will not award you full marks.
Grab a pen and write these 3 major pitfalls down immediately, particularly the tendency to forget boundary conditions when planning your procedures and functions. Let's break these down. First pitfall, confusing cause and effect. Students constantly mix up what triggers a function and what the function actually outputs.
Second pitfall, forgetting boundary conditions and edge cases. When you're writing a procedure to process data, have you actually tested what happens at the extreme edges of your data limits? What happens if the array is completely empty? What happens if the user inputs a massive negative number when the system expects a positive integer? If your module crashes the system, you've failed the design. And third, as we just discussed, providing those generic, non-contextual answers. Do not just regurgitate the textbook. Apply the textbook to the reality of the question.
To avoid these catastrophic errors under pressure, I want you to try using a visual story method to deeply encode these algorithmic concepts into your memory safely. Let's do a quick speed writing mental exercise. Imagine a 30-second timer on your screen right now. Because algorithmic thinking can be incredibly abstract, building a mental, visual narrative of how data flows from the main program, gets passed as a parameter into a function, gets processed, and returns as a value can really anchor your understanding. Think of your main program as a busy corporate manager. That manager hands a specific task and specific files to an employee. That employee is your module. The employee takes those parameters, does the hard work in their own isolated office, and hands a single, completed report back to the manager. That visual makes the difference between local and global scope so much easier to grasp and explain flawlessly under intense exam conditions.
As we wrap up this explainer, I want to give you the final system, the 3 rules that guarantee top marks. Rule 1, command word decoding. Know exactly what the examiner is asking. Rule 2, Peel framework application. Make your point, show evidence, explain, and link. Rule 3, time management matrix. Don't rush like Sam. The 15% of marks available for this topic belong entirely to the students who act like master architects. They plan, they decompose, and they strictly evaluate within the context of the scenario. So take these strategies, apply the structural framework to your next practice paper, and ask yourself this final crucial question. Are you just rushing to write code, or are you truly deconstructing the problem? Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at @AceTheExams_IGCS to excel in your Cambridge examinations. Subscribe right now to Ace the Exams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.